So please welcome Shtub, who will have a talk on performance and fault tolerance while building a modern database.
Okay, hello everyone, and welcome to the talk, Building a Modern Database. Thanks for the introduction, Sven. So my name is Shtub. I'm head of training at ScyllaDB, and my background is as a software engineer. I'm based in Israel, where I am right now, which is also the reason I'm not there in person. I was supposed to arrive, but because of the situation, flights were canceled, so doing it remotely. Before I start, I'll say that I have the chat window open and the questions, and I would like to make the talk as interactive as possible. So feel free to ask questions. Tell me if I'm going too fast or too slow. I'll be keeping an eye on the chat window and the question window. Okay, so the agenda for the talk today is I will start with one of our users' journey with Discord, talking about their problem and how they overcame it. Then I will talk in general about new generation databases, talking a bit about the hardware and how that came to be. After that, I will introduce ScyllaDB, which is a high availability, high performance distributed database. And I will take a deep dive into the architecture, talking about different topics like replication, consistency, cluster nodes, multiple data centers, and hopefully also elasticity if we have enough time. So quite a lot of material. Let me get started. A very useful resource before I dive in is ScyllaDB University. It's at university.scylladb.com. This is our online training and learning resource center. It has quite a lot of material. Everything is completely free, and you can just take some lessons whenever you have some free time. All you have to do is just create a user and get started. Lessons are in the form of videos, slides, text, hands-on labs, and more. So I highly recommend you check that out. Okay, let me start with one of our users, Discord, and their story. So Discord, back in 2015, started out by using MongoDB. They were using a single replica. All the data was stored in memory, so in RAM. In November 2015, they had 100 million messages stored all together, and they were facing latency issues. The amount of data was growing very much, and that data could not be stored any longer on a single replica. They did not want to use multiple replicas with Mongo. And from the get-go, they describe, their engineering team describes that they were using Mongo with the idea of scaling out in the future to another database. In 2017, they decide to do a migration. They look at different solutions. And one of the criteria that they were looking was high throughput and low latency. And they decide to do a migration to Apache Cassandra. Apache Cassandra is an open source, highly available NoSQL database. They were using 12 nodes with a replication factor of 3. And I know I'm using some terms that I didn't explain yet. I'll explain them in just a bit. From a total of 100 million messages, they went to a situation where they had 120 million messages a day, right? So the company was growing fast. It was becoming popular. And while the migration to Cassandra went well, they described the situation, and I'll read the quote. We noticed Cassandra was running 10 seconds, stop the world, garbage collection constantly. So while they would reach very low latencies on average, and they talk about 5 milliseconds per query on average, every once in a while, they would get a query that would take up to 10 seconds, which is very long for a database, a NoSQL database. And that happened for different reasons. Some of them, Apache Cassandra is using Java, and they have garbage collection, which is running in the background. And 10 seconds stop the world queries translates basically to a bad user experience. So imagine you're trying to open the user interface, you're trying to open a channel in Discord, and the UI freezes, nothing happens. So that's not a really good experience. And in 2022, they decide to do something about it, and they're thinking about another migration. By that point, they are running 177 nodes of Cassandra with trillions of messages, so the service continues to grow. And the pain, again, that they were facing was unpredictable performance and maintenance. So imagine maintaining so many nodes in a cluster with unpredictable performance, kept the system on edge. Another quote, "It was a high-toll system. Our on-call team was frequently paged for issues with the database. Latency was unpredictable." Okay. By the way, their journey is described in 2 blog posts, one from 2017, one from 2022, and I put the links on the slides, so you can access the blog post with more details if you're interested. In 2022, they perform a migration from Cassandra to ScyllaDB. They migrate the data. ScyllaDB is actually compatible with Apache Cassandra, so they didn't really have to make any changes to their application. They simply changed the underlying database. They did this without any downtime, so there are different paths to migrate data. Yeah, it's probably out of scope of this talk, but basically you can write to both systems, and then after a while, just stop writing to Cassandra and only read from ScyllaDB. After the migration, they had a situation where 177 nodes were migrated from Cassandra to 72 nodes of ScyllaDB. The P99 latencies were significantly reduced. So from an average of between 40 and 125 milliseconds with Cassandra, they reached a P99 latency of 15 milliseconds with ScyllaDB. So not only did they reduce the number of nodes, the P99 latency was significantly lower. P99 latency, maybe some of you are not familiar with the term. So when we talk about real-time databases, highly performant databases, we typically look at the P90 or P95 or P99 latency. And basically what that means is that is the worst one, say the P99 is the worst 1% case of latencies. Okay, so we might have a very good average, but like with the example that we saw earlier, if every once in a while we have a 10-second query, then that's not great. So we tend to look at the P99 latencies, and we want to have them as low as possible. Okay, let me see if there are any questions so far. No. Okay, so that brings me to new generation databases. I mentioned we're talking about NoSQL databases. Let's go through a brief history. I'm going to make some big jumps here. So at the beginning, databases were using mainframes with the relational data model. SQL became a de facto standard. Think about a big mainframe computer sitting in the first floor of the bank, and all the data is stored there. Then at some point, with the rise of the internet, the amount of data grows exponentially, and data can no longer be stored on one machine. There is also a requirement for data to be distributed for larger scales. And somewhere around the 2000s, NoSQL, sometimes called NewSQL, databases were initially used. They are different from relational databases, and hence the name. I think it's not a great name, but that's what stuck. And then in the 2010s, cloud computing takes off with even more data. And that's when modern databases like ScyllaDB, CockroachDB, as well as others were initiated. And let's understand in terms of hardware why that happened. So what you see in this very dense slide is a timeline of how different hardware measurements scaled according to time. And the number of transistors in the thousands, this is also known as Moore's Law, which probably most of you have heard of. Moore's Law states that every 2 years, the amount of transistors doubles. And this pretty much kept in pace, and Moore's Law still happening. What's interesting in this slide is that at some point, if you can see the blue dots here, so say around 2010, the single thread performance, which was growing in the same way as the transistors, started to plateau. Okay, so you can see it here. It started to plateau together with the frequency. So the reasons for this were physics. I won't get into it, but too much heat was generated, and it was hard to basically squeeze more silicon on the same space. And the solution for that was that the number of logical cores, what you see here in the black, started to rise. Okay, so as these two parameters, the blue and the green, plateaued, the number of logical cores in the black started to rise. And whereas it was common to previously have a single core machine, now even pretty much any laptop that you would purchase would have at least 4 cores. And we see servers that have 128 or 256 cores. So the number of cores goes up significantly. And that is a big change that's happening from 2010 onwards. What else happened in terms of hardware? So I mentioned the number of cores goes higher. RAM becomes cheaper. So we're talking from 2 gigabytes to 2 terabytes. Disk space also becomes cheaper, allowing us to have more disk space. So from 10 gigabytes to 10 terabytes. Seek times become much lower. Networking changes and more. And with all these changes, there was room for databases that would make use of this modern architecture. And that's where ScyllaDB comes in. ScyllaDB was basically started about 10 years ago, so 2014. And it was written to make use of these changes in modern hardware that I just talked about. So I won't go over everything, but ScyllaDB is built in C++. So unlike Apache Cassandra, it doesn't have the Java overhead and garbage collection. It's built very close to the hardware. It does many things on its own. Instead of delegating it to the operating system, it takes many of the things that the operating system would typically do, and it does it on its own to make the best use of the hardware and of the system. It uses a mechanism which is called shard per core. So shard per core basically means that for each core that we have in our server, we assign resources to that core, and those would be CPU, I/O, network, storage, and so on. And that core would be responsible for a subset of our data. Okay, so we don't use the threading model like Apache Cassandra and other databases that were written before. With a shard per core, we have no context switching. We don't have any race for resources, and that significantly improves the performance. Shard-aware drivers, autotuning, clusters with hundreds of nodes and 60 terabyte per node, and billions of operations per second. I'm skipping through this because there's a lot I want to cover. Okay, so that brings me to ScyllaDB. Let me briefly describe what is ScyllaDB and how it works. So I mentioned the Discord use case. I didn't really say what Discord is. I just assumed that most of you would know it, but it's a messaging app, kind of similar to Slack, but a bit different. It's quite popular. So here you can see a list of some of our users, some big names that you probably know. I wouldn't say that we have users from a specific industry. We do have some industries that are popular, like cybersecurity, like ad tech, like gaming. but there are different industries and different use cases. And if you're interested in a specific use case or industry, you can just ask me or have a look on our website where you can find some use cases. So what is ScyllaDB and what are some of the attributes of the database? So ScyllaDB is a NoSQL distributed database that's built with performance and availability in mind. It's compatible with Apache Cassandra and with Amazon DynamoDB, which means that if you have an application running in one of those databases, you can use them. You can use the application pretty much as it is and just change the underlying database to ScyllaDB. And I'll talk about why you would want to do that in just a bit. When I say performance, I'm talking about high throughput. So we're talking about millions and even billions of queries per second. So a very high throughput. And very importantly is latency. I was previously listening to a talk from the people at Bloomberg Engineering about their latency challenges, and that was very interesting. One of the things about latencies is that it's a hard problem. It's a hard engineering problem. Whereas with throughput, typically we can throw more hardware or more money at the problem to increase throughput. With latencies, it doesn't usually work like that. If we want to increase the latency, just throwing money at the problem doesn't really help. And with ScyllaDB, we're talking about single digit P99 latencies. And for the average latency, we're talking about less than 1 millisecond. So it's very fast. And ScyllaDB runs on a global scale, so with multiple data centers, and it is topology aware. There are two different products. One is ScyllaDB Cloud, which is database as a service, just like it sounds. You get the database as a service, and you don't have to worry about administration, backups, repairs, security, and all those things. You just get a database, and you can focus on your application. And then we have the enterprise version, which allows you to run the database on your own. ScyllaDB runs on any cloud, and you can also run it on-prem if that's your thing. So it's quite flexible. I was going to do some poll questions, but since I don't really see you, I'm going to skip that. I even brought these cute plushies. I don't know if you can see it. Yeah, the ScyllaDB plushies. And I was planning to throw them at people that answered correctly. But yeah, it's going to be hard to do that with Zoom. Maybe if you want the plush, you can write me a message and I'll have one shipped to you. Okay, so what we see in this slide is the monitoring stack, which shows us what's happening in a cluster. And here you can have, you can see a link on GitHub to a demo by one of my colleagues, which allows you to start with just a few clicks, 3-node cluster running on AWS on i4i 8x large machines. And just a few clicks, you're going to see this application simulating a workload of more than 1 million requests per second and running at latencies of less than 1 millisecond. Okay, so don't take my word for it. You can run this on your own. Don't do it now, maybe after my talk, but play around with it and see how it works. Okay, I'm not really going to get into competition and migration stories, but maybe let's just look at one example. So we had a user, I talked about Discord. We had another user migrating from Apache Cassandra, and they switched 40 Cassandra nodes to 4 ScyllaDB nodes. And they got 11 times better latencies and 2.5 times cheaper solution. Of course, when you have less hardware, that also makes the solution cheaper and easier to maintain. So again, migration stories from different databases. If you're interested in something specific, ask me later or have a look on our website. Okay, let's take a deep dive into the architecture. Again, if you have questions, please write them in the questions or chat window. I'm keeping an eye on it. No questions. Okay, so I'll talk about architecture, the concepts that I will be covering now. I'm going to use ScyllaDB to sort of demonstrate the concepts, but they are also relevant for other NoSQL databases. Specifically, Apache Cassandra and DynamoDB come to mind, but also others. Okay, so I kept saying cluster, I kept saying node. I never really explained what that means. A node is simply the ScyllaDB software running on a server, on a machine, and a cluster is a bunch of nodes working together to provide service to an application. Okay, we think about it as a node ring. Of course, this is conceptual. And in a production cluster, we have at least 3 nodes working together. Sorry. So 3 nodes working together. And the number of nodes can go all the way to hundreds of nodes working together to provide service. Okay, in this example, we have a 5-node cluster. And I mentioned that ScyllaDB and again, DynamoDB and Apache Cassandra are built with high availability in mind. What does that mean? It means that the database should be up and running at all times, and there is no single point of failure. Okay, so data is replicated across different nodes. We don't have the concept of leader-follower nodes. It used to be called master-slave nodes or any other name you want to call it. All nodes are created equal. All nodes can serve requests, and all nodes hold a part of the database content. And data is replicated. How is that done? It's done according to something called the replication factor, also abbreviated as RF. And RF is something that's defined by you as the database user. You define it per key space and per table. And the replication factor simply determines the number of nodes where data are replicated. Okay, it's important to understand that this is something that happens. However, it's done automatically. So the database does this for you. Let's look at an example. So we have our 5-node cluster from before, and we have a replication factor defined as 3. Again, this is something that you can define according to your requirements. In this case, let's say that this bluish cube represents a piece of data. When we write it to one of the nodes, that data will automatically be replicated to 2 other nodes. Okay, so there are going to be 3 copies of each piece of data. And if I continue to write more data, each piece of data is going to be replicated to 3 different nodes. And it's easy to understand that even if one node, say node 1, goes down, say there is a hardware failure, the other nodes will be able to serve the data that node 1 has. So for the user, it will be transparent. Once the node goes back up, then the data will automatically be streamed from the nodes that were up to the node that previously failed and became available again. And all this happens automatically without the user having to even know about it. Okay, so under the hood, let's understand how this works. Yeah, I could probably give an entire talk just on this, but I'll just touch on it. If you want to learn more, there is an entire course on it on ScyllaDB University. So what happens when we write data? So I didn't mention it, but in ScyllaDB, again, Apache Cassandra and DynamoDB, the data model is called wide column data store. Okay, you can think about the data as a table. So we have rows and columns, like you see here in this table. The columns are pet chip ID, time, and heart rate, and there are different rows. Okay, for each table, we define at least one column that's the partition key. And what the database does is when we read or write data to the database, it performs a partitioner, which is a consistent hash function on the value of the partition key. And according to the given hash, it knows which replica nodes are responsible for this specific piece of data. Okay, so this happens really, really fast. Just run the function, you get the result, and you know which nodes are responsible for the data, either for a read or a write. Okay. Another important concept is the consistency level. So I talked about replication. When we talk about distributed databases in general, and even distributed systems, I would say there's something called the CAP theorem. Probably some of you heard about it. And that theorem states that in distributed systems, we try to achieve 3 different attributes, and these are availability, consistency, and partition tolerance. But there is a trade-off, and we can only give preference to 2 out of those 3 attributes. Okay, in the databases that I mentioned, like ScyllaDB, Cassandra, and DynamoDB, preference is given to availability over consistency. Now, in other databases, like relational databases, say CockroachDB, consistency is given preference over availability. Now, it doesn't mean that these databases are not consistent or not available. There is some trade-off, and we can play around with that by defining the consistency level. So the consistency level is defined as the number of nodes that must acknowledge a read or a write request. Okay, some possible values are 1, quorum, and all. And the consistency can be set per query, per operation. So we might have different queries with different consistency levels. Okay, let me consider an example. So say we have an IoT application and we have some sensor that measures the temperature in the room every second and writes that to the database. So every second we're writing the temperature. And once a day, we're doing some kind of big operation with all the data. We're running some kind of analytics on it and looking at a meaningful result. So maybe in this example that I just described, we can use a lower consistency level when we write the data each second, right? Because even if we miss 1 second, it's not such a big deal. But for the big operation that happens once a day, we would use a higher consistency level to make sure that the data is consistent. Okay? Let's skip this again. And let me just check how we're doing with questions. Again, if you have any questions, please ask in the questions tab. Okay, let's talk about multiple data centers and topology aware. So ScyllaDB is built to work on multiple data centers and to be topology aware. It's even aware of availability zones within a data center. And here what you see is a cluster that's serving an application running on 3 data centers that are spread around the world. Say one is in the US, one is in China, and one is in Africa. My question to you is, why would we want to use multiple data centers? Any idea? If you can answer either in person or in the chat window, why would we want to use multiple data centers for our database? Any idea? Multiple data centers. Why not just use one data center? Anyone have any idea? See if people answer in the chat.
We can give around the microphone. There's someone here who wants to answer.
Anyone want to answer?
Yeah, sure. I mean, for fault tolerance, in case something disastrous happened to the data center in one of the locations, for example. But also for availability, if you want to do lazy reads in North America, you might get lower latency for that as well. So there's more than one reason why you might want to have it.
Okay, so thanks for that. You're right. So low latency and fault tolerance. There's one big other reason to use multiple data centers. Maybe someone has an idea? one more reason. I'll give you a...
Yes, there's someone.
Some countries have legal requirements that the data centers must be housed in the same country that they're operating in. So sometimes it's a legislative thing.
Awesome. Okay, thank you. So that's correct as well. So you got it all correct. Let me kind of summarize what you just said. So the first reason that someone here mentioned was fault tolerance and high availability. If we have multiple data centers, even in the unlikely case that an availability zone or a region or even an entire data center becomes unavailable, say there's an earthquake or a fire, the other data centers can step in and serve requests. So again, high availability and fault tolerance. The second reason that was mentioned here was latency, and that's also correct. So it would make much more sense to serve a user of our application, say a user from the US data center, just because it's physically closer and it would reduce the latency. If I remember correctly, the latency of getting data from China to the US, just because of physics, is about 100 milliseconds. I'm not sure, but somewhere around that. So it's quite a lot. So it makes much more sense to serve a user from a data center that's physically, geographically closer to that user. And the third reason that was also mentioned is for, maybe I will call it regulation reasons, or different jurisdictions might have rules that require that the data of users from within that jurisdiction remain in a specific geographical area. So that's also a valid reason, which, we see becoming more and more important to some users. Okay, so this is an example of the unlikely case of a data center becoming unavailable because of a fire. So it doesn't happen often, but this happened in 2021, so 4 years ago. It was one of the smaller cloud providers. I believe it was in France. And there was a fire. A few million websites went down, became unavailable. One of our users was using ScyllaDB, and they had nodes and a cluster using that data center. But because they were also using other data centers, the users didn't experience any downtime, so they were able to continue providing service. Okay, we're almost out of time, so I prepared a quick wins lab. I'm not going to run it, but let me just quickly show you how it works. So if I click on that link, it's going to take me to the ScyllaDB University website, hopefully. And this is how ScyllaDB University looks like. And you can see we have in this course a bunch of material. If you start the lab, you click on Open Lab. You can do it later. Then this will start actually a virtual machine that runs within your browser. So you don't have to worry about prerequisites or installing anything. It just starts in the browser. And when I launch it, let me maximize the screen here so you can see it better. So let's start the lab. On the right-hand side, you can see different instructions that we can either read the explanations or run those instructions. And on the left-hand side, we have the terminal. And if I run this command, what this does is it starts basically a single node ScyllaDB cluster using Docker just to make it easier. And after I do that, I can check how my cluster is doing. I can start to perform different reads and writes and play around with the database. Okay, so I'm not going to run it right now, but you're more than welcome to check that out afterwards. Let me go back to the slides and maximize. Okay, so that's the quick wins lab. The last topic that I want to talk about is elasticity. So elasticity in ScyllaDB is a relatively new feature, I think, from the last year or so, from ScyllaDB 6.0. So it's based on the Raft consensus algorithm. And what it means in terms of the user is it means that with this feature, we can now scale data or scale a cluster very fast. So that means that we can add or remove nodes to a running cluster, and those additional nodes start serving requests immediately. And this is done with no downtime at all. And when I say that it happens fast, I'm talking about just a few minutes until those new nodes start serving requests. This is based on something called tablets, which is an internal feature of the architecture, which I don't have time to get into. What's important to know is that we can utilize the storage very efficiently. So we're talking about 80 and 90% utilization. When we use the cluster, we can grow it, and we don't even have to grow it in a linear scale. So we can add smaller instances and not necessarily the same type of instance to grow the cluster. Think about an example. Say we have an e-commerce website. We're running a 5-node cluster. Black Friday is coming up. We know that we're going to get more traffic. So maybe a week in advance or a few days in advance, we can add 3 more nodes. The data will automatically be redistributed from the 5 nodes to the 3 new nodes. And now we will have 8 nodes that will be able to serve the extra traffic on Black Friday. I have a quick video that demonstrates how this happened. This is actually from our monitoring stack. So what we see here is we see the tablets on 3 nodes. We add 2 nodes, and these nodes, so the tablets move, they're streamed from the 3 nodes to the 2 new nodes. And as they are streamed, the 2 new nodes can start serving requests. So it doesn't matter if the operation didn't finish yet, and some of the tablets are not completely streamed. Once some of the tablets are streamed, they can start serving requests. So that's elasticity. Again, that's a big topic. I just sort of touched on it. Okay, so maybe to summarize my talk, sweet spot for using ScyllaDB is if you have a requirement for high throughput and low latency, as well as running a distributed cluster for high availability and a high volume of data. If you want to avoid vendor lock-in, so that's common. If we see people that don't want to be locked into a single cloud provider, that's one of the reasons people talk to us. And yeah, if you have an interesting use case, if you think it might be relevant for you, by all means, get in touch. You can just share your use case, and we can tell you if it's a good fit. We can help you test it out. We have training events that happen every month or so. The next one is July 30th. I'm going to speak there. Again, it's completely free. We go into some of these topics more in depth. You can save your spot for free in that link. And that's it pretty much. Thank you, everyone, for attending. And I hope you learned something. And we're hiring, by the way. So if you're looking for a job, get in touch. Thank you.
Thank you very much for the talk. We have like time for one question, so let's have some.
I was just wondering, given that it's very close to bare metal, you said, like how is it normally deployed? Do people buy computers and run it on-prem, or do they rent bare metal computers, or does it run reasonably well on Kubernetes with SSDs attached?
So all of those answers are correct. people use Kubernetes, but the most common way for people to use ScyllaDB, we're seeing more and more people choose ScyllaDB Cloud, so the database as a service offering, just because we're seeing that companies don't want to worry about fine-tuning, upgrading, security hardening, all those things. They just use the database as a service offering. That's the most popular choice that we're seeing people make. However, we still have some users that prefer to run on-prem. Usually it's more like companies that have an engineering team that knows how to run databases very well. They want to fine-tune everything, and we do see some companies using on-prem as well. It's completely up to the user.
All right, thank you very much. Again, have a warm round of applause for Guy, please.